I'm from the University of Latvia. So, so where Latvia is located, I spent a few days in Singapore, and I found that almost nobody knows where Latvia is located. So Latvia is in Europe. Most of the people were asked, are you from Russia? No, we are not from Russia, but we have joint border with Russia. Well, if we compare to Singapore, we are, say, 80 times larger than Singapore, but almost 3 times we have less inhabitants. But what I'm proud of, which I cannot find in other countries, that highest point, or highest, what we are calling mountain, Latvia is 312 meters, but in Singapore it's only between 165 and 182. So we are higher, at least. Now about, so University of Latvia is located in Riga, and now we are, I would say, proud that we are starting. University will be finally, because university is very, buildings are spread in all Riga, and now we are starting to concentrate. There is new building, which is, now it's already all building 215, where we are staying. And now it's the second building, and is started in January 2019. And next year we will start to build third building. Those are for the natural sciences. Those buildings are for natural sciences. Then for human and economical sciences will be third building. Okay, now what I will talk about. I will talk about the working principles of nano-electromechanical systems, or switches. Actually, we are talking about switches, about challenges, about new solutions operation, and then finally about fabrication devices on chip. And we are doing all works. We are fabricating nanowires, characterizing nanowires, and assembling of nanowires, and then doing tests. And we are working, we are trying to making device on chip, but before we worked a lot, and still for characterization, we're using in nanomanipulation in situ inside scanning electron microscope, and there are possibilities to, we can move, say, manipulate four electrodes separately. So, so this is nano-electromechanical switch. There is nanowire, which is switching on off. And why those systems are interesting? Because they have high resonance frequencies in gigahertz and terahertz you can achieve. And they are often used as resonators. Switching speed is very fast, below 1 nanosecond, low power consumption, and they can operate at high and low temperatures, and they are interesting just for harsh environments. And at high temperatures, when you are switching off, in usually it's, semiconductor devices, you have leakage current. When you are switching up, you don't have leakage current. And as element, we are using nanowires, for example, as switching element, because they are one-dimensional, with two properties, and they can be easily produced sometimes. So, working principles. There are a few types. In those just simple switches, you can use single clamp nanowires or double clamp nanowires, and there can be different principles applied for switching on. For single clamp nanowires, you are applying electrostatic field, for example, if you do terminal device, electrostatic field to an electrostatic force will bend nanowire, and plus when you are in close proximity, van der Waals force start to work, and nanowire jumps in contact, and when it's in contact, then elastic force can be used for this to disconnect nanowire from contact. Another way, this is kind of direct switch, and there is also a possibility to use gate. In this case, you're using gate for electrostatic bending nanowire contact, and then this is relay system. How it works, for example, there are potential diagram. If this situation is here, in the center, nanowire is in equilibrium. If you are, moving nanowire from a position up, you have this potential barrier because it's an elastic force. And if you are going closer to the surface, this barrier is lower because close to the surface starts to this van der Waals forces, attractive forces starts to work, and it lowers potential barrier. But it's still potential barrier, and you can decrease this potential barrier by applying voltage, electrostatic force, and nanowire jumps in contact. Something like that. So there are challenges in nanoelectromechanical switches, and one of the challenges is this hysteresis. And hysteresis is related to adhesive forces. If you have this normal switch, you are switching on and nothing happens. But if you are in nanoscale, when nanowire you are applying voltage, and that jump to contact happens. Yes, and nanowire jumps to contact. But then you decrease voltage. Nanowire is not jumping of contact. You see, you have rather large hysteresis, and only till then this hysteresis is related to adhesion, because you have to overcome this adhesion force. So this is one thing. What happens else when nanowire jumps in contact? There is also nanowire when it has also movement parallel to the surface. You have tangential force, and then nanowire is under extra tension. Extra tension, which also should be assumed. And another thing is what happens when small nanowire jumps in contact. Then nanowire jumps in contact. We made such experiments. We find that there is contact strengthening. Adhesion force in contact actually increases when you are applying voltage. And this we tested by a rather simple method. We measured, when we put nanowire in the contact and measured resonance frequency. We are using this second tip to force by electrostatic force by AC electrostatic force to force nanowire to oscillate. And in beginning, this resonance frequency depends on the Young modulus, all parameters. And there is one parameter beta for double clamped beam. It depends on this parameter depends on if it's pinned. It's not fixed end. For pinned and for fixed end, this parameter is different. So for pinned beta 3.9 and for this one 4.7. If during this process this parameter is changing, resonance frequency is changing. And what we find that when we apply voltage and their current density start to increase, we see that resonance frequency shift in resonance frequency. So it means contact is becoming stronger, and this also should be taken in account. No, sorry, the wrong direction. What else? To have enough in switches, to have enough high elastic force in nanowire, you have to bend a lot, and often we need rather high jump in voltages. And if voltage is too high, there, for example, nanowires can completely be destroyed or partly will be destroyed, and it depends on this. Working voltages are depending on different nanowires. For example, bismuth selenide nanowires, they are destroyed at, for example, 5 already after 5 volts, 7 volts. Some nanowires can work till 50, even to 100 volts. So solutions, how to overcome those problems. For example, we shown that you can reduce contact size. For example, if we just decreases contact size from 100 to 45 square nanometers, this hysteresis loop decreases. Yes, for germanium nanowires, there's a problem because they are oxidized, and if they are oxidized, there is usually in SICASAE characteristics they are not conductive, so to 5 or 7 volts. So and because then you need higher jump in voltages or switching on voltages. If you remove oxide layers, so then they are conductive, you can shift this hysteresis loop to the left. What we are doing now on this chip, because on chip, when you are making contacts, usually you have flat surface, flat electrode. If you have flat electrode, you have this contact area larger, and instead of making flat, now we are making kind of triangular system, and then we have very sharp this contact, and it's actually we are trying to decrease this contact area for real device. There are few more tricks. How to decrease jump in contact, or switching on voltage. One way to decrease switching on voltage, we use this resonance. We apply AC plus DC, yes, and we are finding at resonance frequency, nanowire jumps in contact, and then this switch on voltage decreases. We can decrease the switch on voltage 3 times. So this is important for nanowires which are not so which are conductive nanowires. Another way is to have this distance shorter. Then after jumping contact, this elastic force is not sufficient to disconnect nanowire from contact. And then in this case, for example, we used this 2-input nanowire, and when nanowire jumps in contact, it does not disconnect when we remove voltage, but we can apply AC plus DC to this one electrode, and when we are oscillating in this nanowire starts to oscillate in double hum position, and it jumps off contact. And to disconnect, now we have this now single hum 10, and when we are applying oscillation to the single hum 10, and you are getting jump back and forth. And this case also we can decrease this elastic force 10 times. And also another thing, if you have high resistive nanowire, you can in each position you have different levels of current. So, and in principle, also by applying this constant DC, we can, if resonance frequencies for double and single amp are not far away, we can by DC, as this resonance frequency also is changing on DC, we can adjust and find cross points. Then we can switch on and off by the same frequency. Okay. Now I'm moving to synthesis. We are synthesizing ourselves different nanowires. For example, those are bismuth selenide nanobelts actually, crystalline and good. But let's say we are developing this grown from nanoplates and without catalyst. And as you see, number of nanowires is low. Then we played such game that we start to grow those nanowires on anodized aluminum oxide. So it's aluminum oxide, you are getting this nanopore structure, and there is some such shape of the structure, and we find that by using such material as substrate, we can increase this number of nanoribbons 28 times. And when we found that what was interesting, that angles in those ends of nanowires are corresponding to nanoplate growth on different directions. And when we increase this ordering of nanowires, we are getting increase of nanowires. That game, and also we are one simple method to grow of cuprum oxide nanowires. It's very simple. You are just oxidizing foil at high temperatures, but we applied, try to improve this method. We used electric field and plus added water vapors during this beginning of synthesis. And what we got that if it's yellow is it's a simple synthesis, and this is water vapor. We got a distribution of smaller diameters, and we are getting more uniform and smaller diameter of nanowires. Then we also investigating different properties. Those are just because bismuth selenide nanowires are interesting also as topological insulator. It has very nice properties, but mostly we are interested in mechanical properties. We are investigating using this resonance frequency measuring, measuring Young modulus, for example, and also by resonance and also by mechanical bending. And actually, we are getting for different nanowires when we are roping, you have to be careful, especially when you want to work with nanowires with diameters below 100, because, for example, for germanium nanowires, we have, for example, almost not diameter dependent, but for germanium germanium nanowires, for example, by mechanical bending, you are getting higher Young modulus, and by resonance, you are getting almost constant. And this is actually explanation is that in this case you are mostly working with this outer layers, and resonance frequency are getting information about most inner layers. For copper oxide nanowires, both methods, bending and resonance, are giving identical results, and also for higher resonance frequency, for example, it's better to have say, smaller diameter nanowires, but on the other hand, for example, smaller diameter, you are getting this quality factor a bit lower, maybe because of some defects. Okay, there is also for lithium selenide nanowires, when we are using lithium selenide nano, they are not nanowires, but we are nanoribbons, and they are interesting for application, especially when we are using resonance, that we have two resonance frequencies, because as we are rectangular, we are different resonance frequencies, and for example, but part of those nanowires we have terraces, and if you have terraces, then direction of resonance direction of resonance frequencies is changing. If you want to use strongly vertical or parallel movements, you are getting a result movement with under angle. And by analysis, and it's difficult just to see the electromagnetism, for example, those terraces, and we measured resonance to both resonance frequencies and measured also size of those nanowires. And what we got, if a ratio of resonance frequency and ratio of thicknesses, its coefficient is strongly 1, it means that those nanowires are rectangular. If it's different from 1, then it means that we have terraces, and we proved this also experimentally. So now, after all this introduction, how we are using those nanowires in electromechanical switches. This is completely kind of from another area. We use electromechanical switching for improvement, for example, sandwich type devices. When we are growing, for example, lithium selenide thin films, and we want to, and those films, for example, on ITO electrodes, you are not getting flat film, but you are getting growth in different directions, and also growing nanowires, nanoplates, etc. And when we are putting on top electrode, then we measure, say, for example, apply voltage, or when we are moving forward, we see that conductivity start to increase, and then we are going back. You are not going back the same way, but now conductivity is higher. In this case, when you are applying voltage, those nanowires are moving in contact, jumping in contact, and they are not disconnecting. When you are removing voltage, and you see in this slide, when you slide is how you decreasing resistance of your device. So in this case, you can switch. You can adjust conductivity through such arrays of nanowires. So now about switch, about this electromechanical switch. Before I talk mostly about the switch, which we are working in situ to work to have device working on chip. We have to do some tricks. First of all, we are making electrodes, and there is how to put a number of how to put nanowires on those electrodes, and when we used dielectrophoresis, we are using dielectrophoresis when putting solution containing nanowires, and when we apply a AC voltage, you are getting nanowires on contacts. Actually, everything depends on concentration, geometry, voltage, frequency, time, etc. But actually, it's not so ideal how it looks like, because theoretically, there is, how it say, this is theoretical curve, how number of nanowires depends on frequency you are applying on AC. This is theoretical curve, but when you're looking this yield, we can get yield something like 60% till frequency maybe 10 kilohertz, and then by increasing frequency, this yield decreases. But problem there is that if we have such type of contact, we have usually a lot of nanowires in this contact. But we are interested to have only single, and you see number of single contacts in this area is something like few percent only. And if we apply high, and only in interval about 50-100 kilohertz, we are getting, say, more than 10%. So actually, yield, even with this theoretical practical yield to get nanowires contacting between two electrodes is still rather low. It's 10% only. One more problem when you are drying this solution, because of capillary forces, usual nanowires are sticking to the surface. So then you cannot switch because you have already contact, mechanical contact. And then we are using supercritical fluid drying, and in that case we can get nanowires which are freestanding on the surface. We are in cases when we have not enough nanowires in solution. For example, bismuth selenide, we are using nanomanipulations in situ SEM. You see, we are putting nanowire on tip, and then we are putting across. There is already this third electrode, and we are switching on off. But in this case, in this mechanical switching, in manipulation putting, often you see you have nanowires often not straight. It's also not predictable. You can put, and we compared electrical properties of when you are putting nanowires by mechanical or by dielectrophoresis. When we are getting the IV characteristics different, but actually, and there we are looking contact properties, and see that there is in some point it's ohmic contact, and some there is it's where it's space charge limited also area, but those are copper oxide nanowires. And another thing we tested, we put also the metallic electrodes on top, because mechanical contact in this, when you are putting nanowire on the surface, this mechanical contact is not often good, When we put metallic, we got big improvement. But what we can say, if we can use those highly resistive nanowires without additional contact, just use mechanical contact, because this contact resistance of nanowire is higher than the contact resistance. For more conductive nanowires, of course, you can use this better metallization. And there is also this, as I showed before, when you are doing cycling, you can improve also this improve contact resistance, decrease, and by this conductivity increases sometimes. And now finally, this is switch working. So it's two electrodes, and this is gate below. And what we find, not in this case, another case, it's when we are putting two electrodes without this metallization, without fixing contacts, if distance between nanowire is rather large, we have this sliding contact, nanowires is more banded, and in each switching you see the jumping voltage decreases, and then it's at this point it stabilizes. Yes, and stabilized you can already repeatable switching on off, and actually this method, for example, can be good to use before metallization of contact. For example, if we have rather high jumping voltages, because it's rather difficult to adjust this distance because nanowire diameters are varying when you are depositing. Then we can, after a few switching, we can say stop at this point, and then we can do metallization, and then this nanowire switch will be working. I think so. With this, I would like to summarize that we realized this nano-electromechanical switches on in situ and realized on chip, and now we are ongoing work. We are working on chip on single clamp switches. Thank you for your attention.